Okay, welcome. So, good evening. This is our inaugural lecture of the MIT Nanotechnology Public Lecture Series. My name is Carl Berggren. I'm a faculty member in electrical engineering and computer science here at MIT. And before I introduce our speaker, I'd like to thank our sponsors. That's the Research Laboratory of Electronics, the Microsystems Technology Laboratory, MIT's Public Service Center, and the Department of Electrical Engineering and Computer Science for throwing this. Oh, okay, I've got to. We're actually videotaping this for putting on MIT World, and so I have to remember to use the microphone. So first of all, it's a little bit of administrative business, which I'd like to encourage you all to sign up for our email list, which you can get the instructions for simply by emailing nanotech@mit.edu. So, and it'll email you back how to sign up. We're planning to have several of these every year, and so you'll get the announcement of the next one if you do that. There's also comment cards in the back, so if you don't have one now, you can pick one up on your way out, and then sign up, put your email on there, and we'll put you on that list. Okay, so nanotechnology is performed at the nanoscale. Typically, that means dimensions of less than about 100 nanometers, or billionths of a meter. And in recent years, stories in the popular media have really excited our imaginations about nanotechnology. But what is nanotechnology, and what is its significance to society? So in this series, we hope to address these two questions and to be both engaging and accurate in that portrayal. I just want to make the point that nanotechnology research is really an interdisciplinary field. It encompasses electrical engineering, computer science, material science, biology, mechanical engineering, physics, chemistry, you name it. And we'll be bringing people from across those disciplines. We also plan to discuss the applications of these technologies to fields, a huge range, again, computation, health sciences, electronics. But also we want to touch on the potential societal and environmental impacts, because that's a real concern to people, as we know. So tonight's topic will be microrobotics, and I'll confess that my own first exposure to microrobotics came from the popular media. In fact, I recall a particular X-Files episode in which it was discussed. I probably recall it better than I recall some of my college courses. So ever since then, I've found the topic to be very interesting. And though it's not really closely related to what I do in my research, I'm eager to be here and to learn about it myself. So this evening's speaker is particularly well suited to encompass this multidisciplinary aspect of nanotechnology. His research ranges from robotics to biology to computer science. He's a graduate of Yale, and I promise that was not intended as any kind of slight to our colleagues up the river. And then I got his PhD at MIT. He has held faculty positions at Dartmouth and Cornell, and has been a visiting professor at both MIT and Stanford. He's currently the William and Sue Gross Professor of Computer Science at Duke University and a Professor of Biochemistry at the Duke University Medical Center. He's written 4 books and countless papers on research areas such as robotics, microelectromechanical systems, computational biology, graphics, and geometric algorithms. So it's my very great pleasure to welcome back to MIT and to introduce to you Professor Bruce Donald.
Great, thank you, Carl, for the warm introduction, and thank you all for coming before or after your dinner. It's a pleasure to be back here at my alma mater and to see all the great new buildings and new faces. It's good to see everyone thriving. So my talk today is really an excuse to show you videos of microrobots and pictures of microrobots. And if you enjoy that, then my mission has been accomplished. So let me start by telling you a little bit about the people that worked on this project and thanking them, because the graduate students in my lab did a ton of work. And two of them are on the left here, Craig McGray and Igor Paprotny did this work for their theses. Igor hasn't quite finished yet. And then I have two wonderful collaborators. There's Chris Levy, who's a physicist. He's a research assistant professor at Dartmouth who worked on this project for a long time. And Daniela Roos, who's a longtime friend and collaborator of mine going many years back, who's now on the faculty at CSAIL here at MIT. But you should be thinking of these guys in the lab with some help from some more senior people talking with them. So I want to sort of motivate what I'm talking about from a personal point of view. I mean, why should we be interested in microrobotics? And why am I interested in it? So a very biased and personal view. By the way, this is a picture of Daniela when she was a postdoc and I was an assistant professor years ago when we worked together. And this is a conference in robotics, just a kind of milestone of work through time. So years and years ago, and carrying through to today, I've been interested in what you might call distributed robotics. So this is the field that studies issues of parallelism and scale. How can teams of robots cooperate together? And I was particularly interested in robots doing manipulation tasks, so changing the world in some way, moving it around. And so our initial work in this area focused on things that were pretty large. These are mobile robots about 2 to 3 feet high. And as a computer scientist, I was very interested in these issues of parallelism and scale, but you run into sort of a conceptual roadblock, which is you really can't build 100 or 1,000 or 1,000,000 of these guys. And I didn't at the time know anything about microelectromechanical systems, but I said, well, that's clearly the way to do it. We can go into the lab and try to build things that are massively parallel, so hundreds or thousands of robots. And so some of our first work, which took about 10 years, and this was work done with my student Carl Buringer, who's now director of the MEMS lab at the University of Washington, involved what we call ciliary arrays, from the word cilia, little hairs that animals can manipulate things with. So this was basically thousands and thousands, in fact 15,000 independently controllable silicon fingers on a chip. Here's another material called polyimide, which is an organic polymer. And these could manipulate things on top the way a crowd can manipulate a soccer ball with its hands. I guess a more modern analogy would be, it's not moshing, crowd surfing, right, where the hands manipulate. So these are pretty interesting, and this was sort of a record for parallelism and density. There's lots of actuators on a chip at the time. These were done at Cornell, these were done at Stanford. And now, this was a nice exploration of parallelism and distributing a task across a lot of different actuators. But is it a robot? Well, I think it is. But the dream is always to build something more like a car or a bug, something that crawls around and you can steer and is controllable. And we started working on this a few years ago. And this is a talk about making something that's more recognizably like an autonomous robot. And to put this in context, here are some other microrobots. And these are clearly not nano devices. This one gets close, but it's still pretty big. So these are rather large robots that actually do what you might expect a robot to do. You can drive them around and they can do some tasks. This actually, so my student Carl actually took our ciliary array and he turned it upside down so it's kind of like a two-dimensional caterpillar so it can crawl. And that's a nice idea. So this is a nice little micro-robot with thousands and thousands and thousands of legs, which is a good thing. But I was interested in, can we build something much smaller than this? And so that the basic capability you wanted to be able to have was something you could drive around like a car. So in control theory, that's called global controllability, which means if there's a place you want to go, you can get there by some series of maneuvers like parking and steering and backing up and so forth. So I wanted to make something much smaller than these kind of devices. Now, you can get close using this technology called microelectromechanical systems, which basically, in some sense, generalizes the processes that make very large-scale integration circuits, and it is a very, very active area of research. And you can make thin film components like this. So here's some structural components that don't do anything but look nice. Here's the power delivery is a big problem. How do you deliver power to these tiny beasts? And here's some very tiny actuators, but unfortunately these weren't controllable. They jiggle, but you can't actually make them do what you want them to do. So the thing that's complicated is you can make these little components, but how do you integrate them into something that's recognizably a robot under some definition? And that's the big challenge that you face in microrobots, and it's a fundamental engineering or maybe even scientific challenge to think about. So there are many components that you build on in this kind of work, and there's a long sort of line or lineage of this. So I'm going to talk about some of these challenges briefly. Now, one of the hard things is how do you deliver power to tiny things? You can't have a wire to power them, because having a wire on these things in terms of scale, it would be like having a mobile robot this big with a steel beam attached to it. So you just can't do that. So you need some other kind of technique. And there are robots at this scale, but how can we get an order of magnitude smaller? Now, one of the technologies I'll build on are a device called a scratch drive actuator. And I'll tell you all about this, so you don't have to worry if you don't know about this. But the key thing about this actuator is that it's tethered. It does have a wire attached to it. So in some sense, years of work to get rid of one wire, but that wire is sort of essential to make something that's not tethered. Because I think a robot in this scale shouldn't be tethered. And then one of the things that we really want to be able to do with these devices is to assemble larger things. It's very hard to make things at the nanoscale or the microscale. And so self-assembly is a paradigm that's used all the time by biological systems, and why can't we use that for microrobotic systems? That seems like a good idea. So these are sort of some themes I'm talking about today, but mostly I wanted to orient you to kind of what was in place before so you could kind of see how we build on it, what's sort of the scientific legacy that we're trying to add to. Now, what can you do with microrobotics? So this is kind of speculative, so this is why I say possible. There have been a lot of interesting applications proposed. I think that from my point of view, I'm interested in building something that's kind of generic. It's a capability. It's like a car. I mean, the Model T really didn't do very much, but it was pretty clear it was a transportation platform and a hauling platform. If we can make a globally controllable tiny microrobot, then we can haul things around and push them. So some of these that I think are most interesting, I mean, I'm in a medical school, so I'm very interested in, are there biomedical applications? For years and years, I've been interested in manipulation by pushing and pulling things, and that's a good thing to do at the microscale. My colleague Daniela and her students are extremely interested in self-reconfiguring robots that can change shape. And it's possible that little tiny devices like we're making could be used in service of that application. But one of the ones that I'm most interested in is self-assembly, that how can you make a system that sort of builds itself? And if you think such a thing sounds far-fetched, the other half of my lab actually studies these systems from the biological side. And here's one such self-assembling system. Like all proteins and protein complexes, this is self-assembling. So this is the structure of an enzyme that we solved using the experimental technique of X-ray crystallography. It's an enzyme from a waterborne parasite. And this is actually 4 proteins that assemble together to do their job. And the interesting thing about these systems is that they make the assembly themselves. There's no one sort of directing this assembly. So one of the things as you study these kind of biological systems that you learn is that unlike some of the very simple assemblies we can do right now in nanotechnology, which are usually driven by something like hydrophilic and hydrophobic effects, proteins and other biopolymers are extremely active participants in their own self-assembly. And it's possible that that kind of control we could take lessons from that, and we could maybe build nanoscale structures that self-assemble using some of those techniques in the long run. So I'm very interested in the long run at the sort of confluence between biological self-assembly and systems like this and the kind of things that we can build now, which are obviously much more primitive. But there is sort of a theme there that I think converges. So back to the engineering challenges of trying to build microrobots, and what are the things that you have to do in this kind of program? So design is a key issue, which I'll talk about some. I've already mentioned how do you power devices that are this tiny. That's a really essential, difficult problem. There are a lot of problems that have to do with can you design good processes, that is the sort of chemical and, if you will, baking processes used to make these things. The computer science issues typically come in here. How do you control these devices? How do you deal with parallelism? How do you deal with a distributed system like this? And finally, at the end, if you've solved these things, you can start to talk about self-assembly and self-reconfiguring. Now, where are we now? Well, we have some interesting devices. We have some pretty good strategies in this area of control, programming, and distribution. And I think we're just starting to get at the issues of self-assembly and self-reconfiguration at this scale. Obviously, there's been self-reconfiguration at larger scales, but to do it at this scale is quite tricky. So I'm going to sort of talk about some of these challenges, but I'm going to try to do this by showing you mostly pictures so you can get a flavor for kind of how we think about this. So you'll see some symbols on this page that I've put because I figured there might be some people sneaking in from their labs as grad students or postdocs. And if you're the general public that doesn't want to look at the symbols, that's okay. I'll explain it. But I want to sort of say that we have a way of sort of quantifying progress here. And this is sort of a succession of 3 devices, sort of simplifying what's going on. So there's a kind of actuator I haven't told you about called a scratch drive actuator. And what you need to know for now is that it goes in a straight line, and it has tethers. So it only can go in a line that's etched actually on the wafer. And our first step, and this took many years, was to break the tethers. And we made devices that can go in any direction, but they can only go in one line. So you can set them somewhere, but they can only go in straight lines. And then the next, if you will, breakthrough was to get things that could go on curvy paths like this and steer. So it sounds kind of trivial in a way, like for a macro robot, you just put a wheel on it or something, but it's very hard with microrobots. Now and this is sort of kind of how we think about, as engineers, how we think of our devices in terms of their size and how much state they have. But one thing is that if you think of this progression from fixed lines to any lines to any curvy lines in some sense, we try to quantify these by the degrees of freedom that we can reach. So in some sense, the space that you can cover here is you can be on lines, but they're set at the time of fabrication. You can only be on lines that are etched into the road, so to speak. Here you can do arbitrary lines, but they have to be straight, so that's kind of a drag. And here you can do any curves and lines, but there is a turning radius. There's a minimum turning radius. And so this is something more, I think, like a car. There are no tethers, and you can steer it around. And that's really the sort of, if you will, advance that I'm going to talk about today. But I'm going to tell you about this part of our work, too, because it's a step along the way. So it sounds kind of painfully slow, like first you make a car that can only go straight, right? And that takes years. And then what you do is you spend years making it turn. But that's kind of how it works in this area. And there's a technical reason that you'll actually understand by the end that has to do with a limitation of these devices. So these are some pictures of our microrobot. And the rest of the talk is really talking about this device. So this is an optical micrograph. This is a picture through an optical microscope. And this is a picture through the scanning electron microscope, which has some more resolution. Now, if you all are interested, I also made some 1,000 scale models, and you can come down and look at them. So 1,000 is a lot. These are made with FDM machines. So we actually don't use these for prototyping, but they're nice for demos. And this arm is curved up a bit using stress engineering. So it can't do that with FDM, and that's kind of a lesson there. But it's curved up like this. Oops, got it backwards, just like this, sorry. You can look at these later. Just for a comparison with these guys, this is the width of a human hair. So that's pretty small. So definitely come up and play with these, take a look if you like. So let me talk about these a little bit and how these devices work and show you some videos. I'm going to lead you along the path that we took here. So let's talk about going in a straight line first. That's locomotion. See, everything's very much broken down in these funny ways. So again, the sort of goodie that you're trying to get out of this is, can you build something that's an order of magnitude smaller in length and 2 orders of magnitude smaller in mass than the previous big things I showed you? And the task you can do with this is you can push tiny things, like you can push things out of the way, and it's globally controllable, means you can steer it. You can steer it to wherever you want. You can't steer it differentially wherever you want, but you can steer it eventually. So the big challenge we had to face first is, how do you break this tether? How do you make something that doesn't have a wire attached to it but can still go? Now, so this is sort of a close-up of what this looks like, but let me kind of give you an idea like this. So how does a scratch drive actuator work? And this is work from Fujita's lab a long time ago. So the idea is you make a piece of polysilicon like this. So it's a kind of dielectric material. And you have insulation here between a substrate and this thing here, and this little bendy thing. And this isn't drawn to scale. This is about 2 microns high. Now, if I put a wire and attach the wire right there, and then I charge this guy up, he's attracted to this guy here, which is at ground. That's electrostatic attraction. So a lot of things here are going to work electrostatically. So electrostatics, that's static electricity. And you can build microrobots using electrostatics. You can't build washing machines and cars. They only work at this scale. But it'll be attracted down, and then it snaps back up. And it takes a little step forward when it does that. That step is 12 to 20 nanometers, nanometer billionth of a meter. So we're at the nanoscale. And we can do this 20,000 times a second. So 20,000 hertz, which is pretty good. So this will step along nicely if you do this. But you need this wire, right? And here's a picture of the setup. You have the little micro actuator here. And the wire, of course, you don't want a fixed wire, so we make a very stretchy wire, right? This is a stretchy wire like this. And the stretchy wire is going to bend. So let me show you how this works. Here's a video of the real thing going. So he's going to go forward like that, and he's going to snap back when you turn off the power. Now, one thing you'll notice, these guys are essentially massless, right? So basically, you're living in this sort of pre-Galilean universe here where there's no inertia, there's no mass. This guy's going to go forward. He's stepping forward. This is the wire that gives you power. So this is a scratch drive actuator, and this has been done. These are ones we built, but it's basically, all we did really is modify the design in the papers to work on a public foundry. So if you want this, we'll send you the file, and you can pay $3,000 and get 10,000 of these for your bathtub. Okay, so that's a scratch drive actuator. How do we get rid of the tether? So that's sort of the key thing. So here's the idea. So the idea is to build a capacitive coupling, which is based on a capacitor. So what you do is we're going to make a big grid here, but the grid is imbecilically simple. It's just a series of stripes, plus and minus, and we're going to run AC through that. We're going to either insulate the grid or insulate the bottom of the micro actuator. And then we get a capacitive coupling. When there's a charge in here, you get the opposite charge up there, and the guy's attracted. But you don't get current flow because you have an insulator. So this is just a capacitive circuit, and then this guy will flex down. So this is nice. This guy will flex down, and there's no wire. You have a grid, but there's no wire attaching this guy. So that's a good idea. How does this work? Here's an early video. So here's the Microrobot. This is about 60 microns long. So he goes pretty fast. By the way, down here you see the frequency you're driving at. Here he's going to push a piece of dust or little debris out of the way. So here you see the robot actually manipulating its environment. And here it's going not straight. So it's going at an angle there, which is the right. So we can go at different angles. And this raises a different point, which is you want this guy to go sort of the same rate no matter which way he's turning. Right? So that's sort of what you want to have happen here. So it turns out that's sort of a cute little computational problem. I want to point out, well, let me show you that these guys can go pretty fast first. So these guys can go about 2 millimeters a second. So if you scale that to the length, that's about 80 kilometers an hour. That's pretty fast. And here they're actually going, they ran off the wafer and they're running on the control wires on those data points. So these things are pretty quick. So I want to talk about, one of my mentors, Jerry Sussman here at MIT, once said, well, we had this little problem to solve, but at that point it's mere computer science. And what he meant by that was we've actually reduced to something we actually know how to do, which is solve a mathematical problem. And the problem here is how do you design the electrodes so that you get the same power signal at every orientation? And basically, if you fix the size of the grid spacing, and then you consider robots of different actuators of different length and width, you can get variations in power because of that weird spacing, right? You might have the spacing passively timed. So basically, these are the happy places where you have small variation, and these are the bad design points where you have lots of variation. But you can actually write a little computational geometry algorithm, which is very cute, that selects for these points here. And if you select for a good point with little variation, this is what you get in simulation and in practice. So here the axes mean different things. This direction doesn't make any difference. X is that way. Theta is a rotation. Here's x and theta. As I turn and move back and forth, I get very uniform power delivery through the capacitive coupling. So you can design, what you're designing here is the dimensions of the robot relative to the dimensions of the grid so that I get uniform power delivery. And if I do that, then basically you can move in any direction essentially at the same speed. So hidden underneath here, there's some little computational problems that are kind of fun and fun teasers to solve. So we still have a problem. So here's a poor little robot. We call him the Kaiser. And he's struggling to get over these electrodes. You see, it just breaks my heart to have to watch this because it's so difficult for him to do this. Let's watch again. So this is really painful for someone who loves his robots. So he's working as hard as he can. He's struggling to get over these things. And there are a couple of reasons. One is they're a little bit bumpy, but there's a deeper problem we have to solve. And I want to sort of tell you about that. And I think it's kind of a fun problem to think about for engineers and people who like engineering. So the issue is these gaps between the electrodes. So in a gap between the electrodes, you have a fall off in your power delivery because there's nothing there, right? So what's the effect on the robot? Well, this is an exaggerated picture, but you see the tail is much closer to the surface than the bushing over here, which is this part, right? And of course, that effect is quadratic with the distance because electrostatics are quadratic with the distance between the charged things that are charged. And so this is the electrostatic pressure, or the effect of the electrostatic force. And so that if this drops off, this effect is exaggerated at the tail, right? So it's bad if your tail falls in the gap here because the force goes down. Electrostatic, and what you're really interested in here is this angle, which is your flex angle. So if you take this thing here and run it through the kinematics that maps, this length here to this angle, it's even worse. So basically, it's terrible when your tail falls in the gap. The poor Kaiser was trying to go along, but his tail kept falling in the gap, and the electrostatic pressure went to zero, essentially, and so he falls off and staggers along. So we have another cute little computational problem trying to fix this, which is the following. So basically, we make a hexagonal grid, and I can make these grids any way I like, where you have plus and minus like this. So what I'm trying to optimize here is that in the worst possible situation, my tail does not fall entirely along a gap. So here, there's a tail, but it doesn't fall along a gap. It falls along some gaps, but not all. Here's another bad position, but I'm not entirely within a gap. So I reduce the amount that a tail can fall in a gap, and then I still have to do the same trick before optimizing the width and length of the microactuator compared to the spacing of the grid in order to make sure that I get uniform power delivery, consistent applied voltage no matter what the orientation and pose of this is. So this turns out to be another cute little computational problem that you can write down and solve. And if you do that, you get a result like this. So here we've done that. We have this grid, and here we can go in any direction we want, and things go very nicely. So this is beginning to look more like little bugs, but they go in straight lines. So that's what we sort of wanted to have. Now, the other thing we did is we used a different material. So we insulated here with zirconia, which is zirconium dioxide, which is a nice material. So it's called a high K dielectric, so it's a good insulator even when it's very thin. It also has good frictional or tribological properties. It makes things sort of zip along nicely. So there we got motion in all the compass points, and we have something that's beginning to look a little more like a robot, even though it only goes in straight lines. So that's sort of a good thing. By the way, if you all have any questions, make yourself visible and ask them. So I want to sort of say why we want steering, like aside from it being like a car. That's sort of a weak motivation. So we won't be able to individually address robots on this grid, but we can make different species, different kinds, and the different kinds of robots we hope will respond differently to the same signal because their physics is different or because their state is different. And this is actually the way molecules work too. And then you could do assemblies like this if you could steer. So again, everyone of the same species is working in lockstep, but you could maybe build things like this. This, of course, is a simulation made in PowerPoint, not real data, but that's sort of how this kind of thing might work. But let's see before we do steering how far we can get without steering. You actually can get surprisingly far. So I'm going to use a trick that I'll define later called voltage selective actuation, which means by changing the voltage of the pulses, I can make some guys go and some not. And I can do a primitive little assembly like this. Notice this one moves last because of the voltage selective actuation. So I'm going to build a little structure here by moving these guys all at once, and they're going to interact through compliance to do a simple little assembly. Not the kind of assembly you would get written up in the New York Times for, but still an assembly nevertheless. So this is 80 microns on a side here. This is 60 here. So that's not a trivial thing to get to happen. So because you have compliance, even with linear actuators that only go straight, you can actually put together a little shape like this, which is nice. But we can do much more if we can turn. And so I want to turn now, so to speak, to how we make this thing steer. So I've given you sort of a flavor of how you can design a thing without a tether that moves in straight lines. Probably it's an actuator, not a robot. Here's a thing that's more like a robot. So let's talk about the steering. So here's the arm here like this, and here's a close-up of the arm. This is the optical microscope picture. Here, a close-up scanning electron microscope. And what you can see is this has an interesting design. It's curved off the wafer like this, and it has a little stylus on the end to prevent sticking. So here's basically the deal, is that this part here, and you all can come up and look at these afterwards, this part here is going to creep forward, right? And this is up in the air a little bit. Now, I'm going to make them independently controllable using some magic that I will define. And when this guy wants to turn, he's going to put this guy down on the wafer. And he's going to turn around that point the way if you're riding an off-road motorcycle, you put your foot down to skid around a turn. Right, you put your foot down, you skid around on your foot, and then you bring it back up. So forward, put this down, skid around it. So that's what I want to do, but I have to make these independently actuatable. So I can fabricate these, but it's actually a little bit non-trivial to do this. So let me talk about that a little bit. So that's what I want. And again, we're getting a pretty fine scale here. This, the feature size down here that's like a micron or so. Okay. So I want to just give you a little flavor for why you can do a thing like this. So the one thing that's really great about these scale models is that the whole thing is connected. It's one piece of plastic. But the MEMS device is like that too. It's one piece of conductive polysilicon. So you have this thing where you don't have electrical isolation between the two actuators. So the challenge we have to face is how can you independently control two things that are mechanically connected and electrically connected? How can you do that? So we have to find some way to basically get around that problem. And the way we're getting around it is something like this. So this is the most studied problem in microelectromechanical systems. It's the problem of a cantilever. So, and this is actually not the model we use. This is an early model that kind of has the right qualitative features, but it has the right idea. So if you have a silicon cantilever like this, like my arm like this, and it's attracted to a substrate like this because there's a charge differential, if you crank up that charge, it's going to snap down eventually, and it's going to come, as you can see here, it's going to touch that guy. Now, when it does that, it's a function of various things like this gap and what the charges are. And here's a model for what the voltage at which it snapped down is. But the key thing here is if you start the voltage out at 0 and you crank it up, it's going to sit there for a while, and then it's going to snap down. And that's the key thing. So the things that are important here are this gap. There's this cubic guy. There's some area. There's a permittivity of dielectric constant thing here. But this gap is very important. And it's, because it's cubed here, it has a really big effect here. So the interesting thing about these systems is if I have snapped down my arm, and now I back off the voltage, it doesn't come right back, right? It sits there for a while, and then it comes back. And that's called hysteresis. And that's how I'm going to put state in my system. So here's a picture of that. This is the release or snap up voltage. And this is also strongly conditioned upon these gaps and the area and things like that. But see, the thing that's key about this is that you can model this, so you can design something. But the point is that the release and snap down voltages are different. And the way to think about that is what you want to optimize is the ratio snap down to snap up like this. So the key point here is, here's a little graph. Here's my deflection. This is the height of my finger over here like this, and here we have voltage. So as I start up here and I crank down the voltage, crank the voltage to make it larger, I'm just going to sit there for a while, and then boom, I'm down. So I back off the voltage. I'm going like this, and then all of a sudden I come back up. So I'm going to store state in these loops, this hysteresis band here like that. And that's the key thing here, if I can optimize this. Now, that's the idea. Now, what's the practice? So all MEMS processes, but particularly the ones we use, are very, very good at controlling in fabrication the sort of x and y dimensions of your devices. So those are your dimensions like this here, like x and y and so forth. They're really lousy at controlling the z dimension. And that's a huge problem. Like, how do you do that? So what we do is we make them, and then we post-process them using what's called stress engineering to try to get this gap exactly the right height. So in other words, to optimize this snap ratio here, the little high school algebra here, to optimize this, I have to make these gaps exactly right. So I need fine control over that, so I have to invent a process that allows me to do that control. And that's going to be stress engineering using chromium. And how does that work? Well, basically, here's a little test device. I'm going to put chromium on these guys after I've made them, and then I'm going to bake this in various ways, and then it's going to curl up. And by depositing this different amounts of chromium, different conditions, I can get really any shape that I want within limits, and stress engineering is going to give me really fine tuning. So by doing that, I can stress engineer these devices to have really good snap ratios, which is what I want. Okay, so that I want to tell you, before I show you some videos of this, just a little more about the processes to make these things. And this is sort of a truly amazing set of technologies. And this is my student Igor in our lab working hard. So let me just sort of point out some of the things that we have to do. And I think it's just interesting to sort of see this. I won't go in any depth about this. So if you look at this, we make the first half of these devices at a foundry, and then we post-process them in our lab. And the chromium step is one of those post-processing things. But here's kind of what this looks like if you haven't seen MEMS before. So with these MEMS processes, MEMS is Microelectromechanical Systems, as sort of a parity, you can deposit stuff, and you can etch stuff away, and you can selectively etch certain materials, and you can etch either straight down or you can etch in all directions. And when we make these devices, they are made on a bed of this silicon dioxide or glass here. And these are different materials. This is typically polysilicon. So when they come like this, then we have to etch afterwards to release this thing. And you see, we get quite fine control. So for example, here's the under etch of the stylus. But basically, the way this happens is this is built up. We start with a substrate, and you deposit things and etch things away to get these shapes. And when they come to you, when they're done, then you have to release them by etching away the sacrificial material. So it's pretty interesting to do this. And I think it's interesting for you to see kind of what these various steps are that actually make these devices. And of course, the stress engineering happens in this area here. That's where we're depositing the chromium in order to pull things up. Now, in addition to making the microrobots, we have to make what we sometimes call the environments, or these fields that they live on. And that seems kind of straightforward because it's just this grid. But actually, there's sort of some cute things I thought you might like to see about that, which has to do with the deposition of the zirconium. So I drew a little picture so you could see it. So this stuff over here is routine for sort of electrical engineers. This is etching an interesting shaped grid. So we can get good control over our wires. That's not a hard thing to do. But this part is a little bit interesting. And again, this is straightforward to someone in the field, but I think to you all it might be kind of cool. So zirconium's a metal, and you get it into this plasma phase by shooting it with an E-beam. Now, if you just do that with your electron gun, just straight on, which you would actually never do, as you will see, it goes into the phase and it coats everything in its little chamber, including the electron gun, right? So that's not the way you do it. So you have like a wall here or something, and you actually shoot it into the cup this way, and you're trying to coat this guy. And you actually bend the electron beam around like this with a focusing magnet. So, I grew up on Star Trek. I think it's pretty cool that what we're really doing here is we're bending an electron beam around a corner in order to do our process. And that's a routine thing that we do every day. So it's kind of a neat trick. So there are all these sort of neat high-tech tricks that, you have to do this stuff. And they're really kind of at the limits of, everyday physics. There's somewhere between everyday physics and real physics. Okay. So if we can do all that and make these devices, then we can start to talk about control of these kind of things. So how might this work? So I'm going to describe this by literally waving my hands, or waving my pointer in this case. I can't quite reach. So there are 4 states here, right? So the scratch drive, which is the little actuator part, it can be stressed or it can be relaxed. And the steering arm can be up or down, right? Because I got this hysteresis thing. And the way I design this is because I can control these gaps. I can really make these release and snap-down voltages anything I want within reason. And so the trick that I'm going to do is I'm going to make the scratch drive. This is USD8, untethered scratch drive actuator. I'm going to make these guys in here, okay? This is voltage, small to big. They're going to be bracketed by the release and the snap-down voltages for the steering arm, right? So I can actuate the scratch drive actuator in here without disturbing the state of the steering arm. So if I could point to this, I'd wave my hands, but instead I'm going to wave my laser pointer in an irritating way. So here's how I go straight. I release the steering arm, and then I come up here, and I stress the scratch drive, and then I do this at 20,000 hertz, right? Now if I want to turn, I go up here, I put the arm down. Now I go down here, and I turn, and the arm stays down. And now I release the arm, I go down here, and then I keep going. So that's the entire control strategy. Well, not quite, but pretty much the whole control strategy. So one of the things is you got all these charges, so things tend to charge up and not work. And so what we have to do is we have to minimize charge trapping in these dielectrics. So you minimize the duty cycles here, like this. And the other thing you do is you have to flip the flip the charge cycle or polarization. So we're going to do lots of plus charges for about 125 milliseconds, then I flip the whole thing over. And it only cares about charge differential, so that's fine. So I do this, and then I just flip it over like that. That's fine. Same thing for turning. So there's some subtleties to getting this to work, but that's sort of the right idea. That's the program that drives this thing, basically. That's the idea. OK, so how does this work? So here's going straight, right? This is the primitive motions. There's the primitive up there. So my advisor, who's still here at MIT, Tomás Lozano Perez, said I should never use the word primitive because it meant an old guy in a cave. So I had to put one on just because I was speaking here. OK, so we can go straight, we can turn. Here's some data. So straight is pretty straight, turning is pretty turny. So that's what it looks like. That's the right thing. And that's a formal scientific assessment of those statistics, by the way. That's what we call it. Pretty turny is what we call that. All right. It's not as fast as the guys without the arms. The arms slow it down, but it's still pretty fast for these devices. That's quite speedy. Now, we don't have to always turn or go straight. We can interleave these, right? We can surely, what we do is you interleave the commands to go straight and go curvy, right? You do that at some frequency, and you can get paths that look like this. So we can get different radiuses here, radii. So there's a minimum turning radius of 175 microns, roughly, for a steering arm this size. And then I can get anything bigger than that just by doing this. So there, I get some paths like that. Now, teleoperation is when there's someone looking at this and telling it where to go by just flipping a switch between the different waveforms. And so here it's spelling out the Duke D. Now, one thing you notice about these devices, they can only turn left. Right? That seems like kind of a bug, doesn't it? So we're working on that one. So it can turn left. But the thing is, it's not actually that big a deal. So you can actually turn, if you want to go the other way, you do a jug handle, right? So there you go. So it actually makes a better demo. So here's the correction, right? It's a teleoperation, means you're looking at that. So it's going to make a right turn by going around the jug handle each time, right? But it's not a bad thing to show that the device is controllable. So there it's going to go around like that. And it's going to do a couple more here. So it's unusual to get this degree of controllability with things that are this small, and of course there's no tether. So that's kind of what we wanted. So that's sort of that's sort of where we are. Now, there's lots more. I want to give you a flavor for it. There are lots of other things you can do, and I want to tell you sort of some directions here. So one of the things you can try to do is, how about someone who can turn left and right? That's nice. So we've done that. And I'm going to tell you how. Backing up would be nice. If you could back up, you actually get non-holonomic system. You get parking. You get small-time local controllability, which means you can move in any direction you like. Building things, that you get snapped together. So the thing is that I think that the most interesting thing to tell you about is parallelism. But let me sort of speak to these a little bit. So what else can we do with this sort of scheme? So how about 3 cantilevers? So if I have 3 cantilevers, I can control 3 independent actuators. And if I nest their hysteresis loops, as shown in the simulation, I can reach all these different states. So this is just a little simulation of going through not just 2 of these hysteresis bands, but 3 that are nested within here. And then I can go through all of these guys, and I can get 8 states instead of just 4 states, and that would be a good thing. So this is sort of the theory of how you go through a control system like that. What's the practice? Well, here's a device that doesn't do anything except test the idea. So here are 3 cantilevers with different gaps. And here's a state diagram that corresponds to, counting in binary up to 7, basically, or up to 8. So basically, these are all the transitions. So with this device, we're able to go through this entire state diagram and count. But could we use that on a microrobot? So you see what we do. You put this one down, that's 1, then you put this one down, and so forth. So here is the bidirectional robot. Here's how this works. So basically, one cantilever is this, one's A and one's B, and the different states correspond to, are you going forward, are you turning left, are you turning right? And basically, so forward actuation is going back and forth like this, and then you do some transition to turn like that, and so forth. So that's sort of how that would work. So that actually is doable, which is kind of neat. But I think it's kind of cooler for you all to see concurrent operation. So I'm going to kind of concentrate on that. So what about 2 or more robots? That's a good thing to do. So here we have exactly the same state diagram. So we're very parsimonious in how much work we're doing, i.e. we're really lazy. And so here we have the same state diagram. And here you see we've got this one is, they can, basically what behaviors can it have? It can go forward, both forward at the same time. One can turn while the other goes straight. That first one can go straight while the other turns, or they can turn at the same time. So we'd like to get these 4 behaviors working together. And let me show you kind of how we're doing on that project. So I'm going to show you a video. It works a little bit better outside of PowerPoint, so I'm going to do it that way. But what I want to say about this is that these videos are each about a minute, and they're kind of less sound-bitey, because this is sort of, the bleeding edge. But I think you'll probably still get something out of them. So let's see what we can do. So again, here they're both turning at the same time. So these are different, if you will, species, right? So they're turning at the same time, different rates, because they have different length arms, basically, and different characteristics. Now what's going to happen is this one goes straight while that one turns. So I'm going to give you all 4 behaviors here of this independent control, right? And now we're going to have them both go straight at the same time. And now they both turn. So we're going to get all 4 of these. So what's kind of interesting about this, let's see, and now this one turns while that one goes straight. And that's the end of the movie. So what's, I think, kind of cute about this is that we have global power delivery, we have a global control signal, but we're getting very selective and independent control of these guys through our scheme. And I think that, is kind of a cool thing to do. Let me show you another one. Whoops, I don't want that. I want this. Yeah. At least it isn't some embarrassing thing. Let's try that. Okay, so I do have a video on the bidirectional robot. It's kind of straightforward, it does it. I want to show you sort of the power of this by showing you how you can assemble a bidirectional robot from 2 left-handed and a right-handed guy that come together. And it's sort of more suggestive than conclusive, but I think you might sort of, enjoy seeing this. So let's take a look. So again, this is a little sketchy in some ways. So here we have 2 guys. It's going to be similar to before, but at the end they're going to interact by sort of assembling. So how would they assemble? Obviously, in some sense, they're going to try to come together and build a little structure. And the interesting thing about that is because the dynamics are coupled, once they build that structure, then they're going to have a different behavior at the end. And we're going to sort of see that. So one of the things that's interesting about this is another sort of computer science kind of viewpoint, is, okay, I want to make an assembly and I can control these. Well, how do I actually control them to do what I want? It's a complicated system where you don't have all the degrees of freedom available. So in some sense, if you did this by trial and error, you'd basically be trying to crash them into each other in creative ways so they'd interact. Now, in fact, we have a planning algorithm that more or less works to try to plan out these strategies to minimize our experimental time. But you're probably wondering, well, when is it going to build something? They're just sort of orbiting. So we're kind of waiting for that to happen. So soon, there'll be some actual interaction here. And then we'll see a sort of a primitive form of assembly here as these guys come together. Here they come together. Now we have sort of, if you will, a bidirectional actuator. And there actually has a different dynamics as it goes off together like that. So now those are basically, in some sense, instead of fabricating a bidirectional actuator from scratch, we can sort of build one out of 2 components. So that's the kind of thing that we're sort of interested in doing. Now, let's see, where do I want to go here? I don't want that. Now, one tends to think about these robots in very personal terms. And, I think when they're doing things as complicated, they sort of look like little life forms. Maybe not. But to try to convince you that of that viewpoint, here's a little robot ballet. It's very romantic if you look at it in the right sense. So this is, again, about a minute long. peacefully going off for some time together. Okay. So I'd like to spend a few minutes kind of speculating on where we are. So, as robotics or MEMS people, we tend to think of things in these terms. Quantifiably, what do we have in terms of size and state and controllability? And from this point of view, I'd argue that this is a little micro-robot. But, you might not agree. So let me preempt that criticism by stating some objections. And I think that the real point of this is to say, hey, what is a robot and what are they good for? And I think that's a good discussion to have. But it's nice to actually have some robots on the table, or at least 10,000 scale models of them on the table before, to have some data to think about that. So it's a micro-robot because it does all these things, and that makes me happy, that's that. But someone might say, I don't really think it's as small as you say it is because I don't like this grid. This grid is huge, right? It's got this big wafer. And, it's not completely autonomous. It's got a grid behind it. Now, this makes me very unhappy. I don't like this criticism, and there's not a lot I can say. But what I will say is, well, there's a solar-powered robot, and I usually don't think of its mass as including the mass of the sun. And I am not a robot, but I'm a life form that breathes oxygen, and I usually count my mass as being around 175 pounds, and I usually do not count the weight of the atmosphere. So I think that's a little unfair in some sense. I don't know where it's written down that you have to carry your power supply around with you all the time, but okay. So there are things you can say, but they're sort of ad hominem. So on the other hand, if I have hundreds of microrobots and they're covering the wafer, then I'm schizophrenic. I don't mind calling the wafer part of the robot because I actually really like multiple robots. That's kind of what I want to do. So in other words, I think maybe the right measure is the ratio of the robots to the size of the grid or something. So somehow in this context, I don't mind it because basically the area of the robots is similar to the area of the wafer. But I object to it over here. So another way of looking at what we have is a very mechanical engineering control way of thinking about it. And what we've really built, and this is a joint. So we built what's called a rouleau pair. It's a lower pair. It's two things that have 3 degrees of freedom relative to each other. They can translate in 2 dimensions, and they can rotate. And I actually really like this characterization because it really says exactly what we've built. We built a completely controllable joint. And then since joints are useful everywhere in science, engineering, and technology, therefore, we can kind of quantify what we have. So I actually think that's another way of saying what this device is. It's not quite as exciting as robot, but it's, I think, a good thing. Someone might say, well, what you really built is a smart part. It's a very clever part, but really the intelligence is in the field, right? You built a part that reacts to the field, and it's moving around in this way, and maybe you could do other things. And I don't like this at all. This makes me very unhappy. So I think it's more of an actuator, or at least I think it's a robot. It's at least an actuator. I don't think it's a smart part. But on the other hand, here's the schizophrenic part. I spent many years with my student Carl, and what we tried to do was we basically tried to characterize extremely fancy vector fields that could be used to manipulate parts that were passive. And there's a deep theory there and a lot of deep practice as well. So somehow the exploration of the kind of fancy fields one would have kind of makes me happy. But the idea that the field is simple and the part is smart kind of makes me unhappy. So I still like this, but there are different ways of looking at this, and they really, this isn't really a personal thing. Really, this gets down to what is a robot. And I think it should be based on tasks, like global controllability and quantifiable properties like size. But I think this gets down to what your notion of what are you trying to build, what is a robot at this level. Now, there's another way to resolve these issues, which is by authority. And so here's an authority. This is someone at Berkeley. Now, there's lots of things you could say about this. So, if you're kind of not in the field, you could say, oh, that's great, this Donald guy has someone saying it's really a robot. So that's good, right? There's someone who supports him. Let me tell you what's really going on here. So he does say that, and that's nice, right? But what he's really saying is this. He's saying, Those guys built a really small thing, and we're trying to build really small things. And I want to tell you that mine is actually smaller if you look at it right. So what he's saying in here, dry environment, he's saying he's built smaller things that work in the water. That's what this means. That's what this means, really. This is a good guy, right? But people are staking out their turf. So let me tell you what, so let me respond to that. So it's true, there are smaller things that work in the water. Now, the smaller things in the water are both more robots and less robots. They're more robots because they do more actuation. They float around, and they can grab onto things, do chemical reactions, grab onto cells. They do clever stuff, but they're not controllable. They drift, right? So it depends on what you want. If you want something you can steer like a car, like Fantastic Voyage, you won't find it at Berkeley. But if you want something that has actuators that will give you global controllability, I mean, you can actually do reactions, right? Our thing doesn't do any chemical reactions. So there's a trade-off between sort of the effectors that are glued to this thing and the ability to globally pose it. But when you read these things, I mean, I didn't give you the quotes from the New York Times, which are quite a bit more ridiculous than this, but there's always something to parse here, and it's part of the scientific culture. And by the way, this is all friendly stuff. So you can imagine the unfriendly stuff. Okay. So this part actually isn't technical, but there are some words on here. I want to philosophize a little bit about the control model. So in this system, everyone's getting the same power, and everyone's getting the same control because the power signal is multiplexing as the control signal. And that seems kind of inelegant from kind of an AI or distributed robotics point of view, because why should we live that way? Why can't we individually control them? I mean, years ago when you built robots, you couldn't have, Unix running on each robot. Now you can't. So can we dream about that? I think we can. But let me argue that there are a lot of systems that have the same flavor, and they're typically smaller than the ones we're talking about. So if you look at things like this, like cells or neuroscience or protein folding, these all have the same power source, and it's global. All you can do is change things globally. You can't go in and say, typically can't go in and say that protein gets some power and this one doesn't. And then the idea that you can control things individually, I mean, it's not a network, right? You can only really broadcast. You can't target things. Everything's through diffusion. And so in these systems, you basically are sending out control using different techniques, like it's like a diffusion process. And the entities in the bath, so to speak, are responding differently because they have different physics and because they have different state. Now, I know this is the way cells work, and I know this is the way proteins and biopolymers work. We're bigger than that, but I think this is the control paradigm that works at that scale. And so I think we could probably take what we're doing and go down a few more orders of magnitude, but ultimately I think that this kind of control scheme, global power delivery and global control and selective response, is really all you can do at the nanoscale. And so the fact that we have this rich vocabulary of control, in fact, these robots are much more controllable than other robots of even comparable scales, means we can explore control paradigms where we can't individually address the devices. And I think we'll need to do that as we get smaller and smaller. So this is sort of a, it's kind of a simulation of what we'll have to do eventually, but also hopefully useful immediately. Now, again, here are pictures of devices that I didn't build. Well, actually, I did build these because this is protein engineering. So, but I had someplace to start from. So these are devices that have global power delivery, and they have global control and selective response. So I think our devices doing that is not an unreasonable thing as a place to explore. Now, how close are our devices to things like this? They're a fair ways off, but it's not inconceivable. So this is a scratch drive actuator here. This is just the one of the linear kinds. And this is the blood cells from my student, Craig. So I usually don't show this to prospective students because they think they might have to work too hard in the lab and actually give their blood for the project, but Craig did. So you can see that we're it's about 10 or 20 of these will cover this. So we're at the scale where we could start to begin interacting with cells within maybe the next 10 years, I think. And that's exciting. Now, there are lots of other MEMS projects that do interact with cells directly. I'm talking about our devices. But that's where we'd like to go in the future, is to ask, can these be used to assist in laboratory techniques like protein design and manipulation of cells and biomedical engineering. So I want to just sort of conclude by saying what you might take away, which is that I think there's a lot of promise for micro and nanotechnology, and that you can be very application-driven, but I also think it's kind of interesting to be task-driven and to say, well, if you really wanted to build a car, what does it have to do? It has to have controllability, and it drives you to some very interesting engineering problems that I think are generally applicable. And some of these are, can you develop new processes? Can you develop new control paradigms? Can you develop new devices in some sense? And putting these all together does result in things that are like microrobots and are much smaller by 1 or 2 orders of magnitude than existing systems that do similar kinds of jobs. And I think that in the next probably 5 or 10 years, we'll see these kind of things reduced to be even smaller and hopefully be able to do some useful things in the laboratory and in the clinic. And that's what I hope to be talking to you about 10 years from now. So finally, I want to acknowledge my collaborators and some people that helped, but particularly the graduate students, Craig and Igor, who worked so hard on that, my collaborators, Chris and Daniela. I'd like to thank our funders, and I'd like to thank you for coming out and listening to a talk in the evening. Thanks very much. Thank you.
So our speaker has very graciously agreed to take a few questions after the talk. So are there any questions? Yes. Actually,
I wanted to know if the robots and the environment were fabricated on the same chip or different chips, and could you plop robots from the outside onto the arena?
Those are great questions. You're playing into my hands. So different chips. So how do you set up experiments? You're asking essentially. How do you do that? So how many of you all built models as a kid? And by models I mean aircraft carrier Enterprise. Those plastic models, right? So how the parts came. The parts came in these with these sacrificial things. They had a ring around the end, and the parts dangled off, and you broke them off, right? So that's what we do. We call them transfer frames. By the way, this took years to do, and it's probably not even publishable. So it's just you have to do is one of the things. So what we do is, when you make these devices, you first of all, you make them attached to other stuff. But the things that attach them, which are like little wires, have designed-in flaws that will break. And so one of the things you can do is you can make a tethered scratch drive actuator here. Remember, the wafer's this way. So this guy's tethered, and he'll go back and forth on his rails. Then I have a sacrificial tether out here like this to my untethered scratch drive actuator. And I have him on a grid. And so when these guys want to be released, what I can do is I can say, this guy gets the control signal to just flatten down and stick to the substrate. This guy walks ahead, he breaks the tether, and then this guy is now free to go. So that works if you're in one place. So what I do now is I make all my parts that I want to arrange. I can even design the experiment ahead of time. Instead of all these parts at the right positions and orientations, and they have these sacrificial tethers. And these things are relatively big. They could be like a couple of millimeters across. You could easily pick them up with micrometers. So I make this frame, and I release the thing, and I pick it up with micrometers, or maybe I get one of my MD PhD students who has good hands from all his surgery training. They take them and they transfer it to the other frame, other die. The other die has little nicks in it, so things will align. And when you put and they also give power. So when you put those nicks in, it aligns because it has fixtures there. You snap those things down, turn on the power, and they all walk away, and you rip the frame up. So you can do this, and you can get these massively parallel experiments going all at once. So it's a nice way to do it. Now, if you have really good hands, you can actually pick up individual actuators when they run off the wafer and put them back on. But that's a dicey process, and you could scratch it. So what you really want is the transfer frames. So there's a whole sort of behind-the-scenes technology to do that. Great question.
Yes. Actually, if you wouldn't mind asking the question at the microphone, that'd be great. Thanks.
Hi. The power is tethered, and the intelligence is tethered, because the intelligence, in terms of how the thing moves around, I'm not in the field, so I'm trying to ask my question is, But are you thinking about ways to allow the robot to make the decisions on where it goes, when it goes, by signaling somehow back to the power source through the grid?
Yeah, we're working on that. It's going to be a while. So what I'd say is the kind of capability that we're trying to get now is teleoperation. So you turn on the news and they're sending a robot down to look at, the Titanic. Well, a lot of us in the field don't really call it a robot, right? It's got a wire on it, and you're sending it signals. It's teleoperated by someone up on the ship. Maybe it's a robot, I don't know. But when I think of robot, I think it doesn't have the wire and it has intelligence on board. So these guys have no intelligence on board, but they don't have a wire. So it's, it's a series of steps towards getting a thing that's truly autonomous. So what would we have to do that? Well, we'd have to be able to put some circuitry on the robot. And that could be done. It's kind of a complicated process to put circuitry on top of this whole process. But if you could fabricate transistors on top of it, then you could have it make some decisions possibly. So we hope to do that, but it'll probably be years. There are things that have been made that have the right complexity, but just not in sort of this untethered setting. So it's probably technologically feasible.
Further questions? Yes. Can I ask you to, or I can actually bring you this here.
Sure. So my question is, if you put a knife blade or something like this onto this, is there some material that it could cut and make something?
It's a good question. Probably. We're still trying to figure out the mechanics of these devices. I mean, they could definitely rearrange things and push them around. Could it cut something? Possibly. The thing is that a knife blade actually isn't that sharp at this scale. So to get something that is really pointy enough actually requires some fairly fancy engineering. So basically, the way that I would want to do it is have something made out of single crystal silicon, which can really go down to almost atomic lengths, and then you might be able to pierce a cell or something like that. Probably the application you're looking for is probably in neuroscience, where you're trying to align electrodes for, say, recording in awake-behaving primates really exactly. And that probably is coming. Basically, microactuators of arrays of those needles could come. I don't know why you need to have it untethered and autonomous, though, but possibly. Maybe you could.
Given the public's concern about nanotechnology as expressed in certain books and science fiction, they may be interested in why the Department of Homeland Security is funding the work.
Yeah, that's a good question. You always tell a different story to different audiences, and they had a particular story they were interested in. So they came to me, and they said, well, we have all this security stuff, but it's based on computers. What about mechanical security? So at Sandia, they have a lock. It's a MEMS lock for nuclear warheads. And the way it works is, if you look at it, it's got gears, and it's got, it's a combination lock, basically. And if you put in the wrong combination, then it locks up in a state that it can't be unjammed. Now, the nice thing about devices like this, like mechanical devices, is that you can make what we call one-way functions very easily. In other words, it's very easy to bollocks them up so that you can get in a state that locks up and you can't get out of. We call them motion diodes. So they like that device, but the problem is that if you look at it, you can tell what the combination is. So they said, can you build something that's kind of difficult to figure out? So something like a digital signature made out of mechanical things. And I said, you want me to build a Babbage engine out of MEMS? That's what I said. A Turing machine out of MEMS? And they said, well, not exactly, but what could you do? So the idea is something like this. Suppose that I had some of these robots, and these robots have very specific device characteristics, right? I mean, they'll only do what they do because they have exactly the right physics. So I think that's pretty clear from these gap arguments that I made. So actually Carl and I haven't met in person except for today. So how do I know he's him, and how does he know I'm me? So what we could have done is I could have brought 100,000 of my microrobots, and he could have bought 100,000 of his microrobots. And they're all carefully designed, and we put them in a trusted field. And then the way they're designed, they self-assemble into a circuit only if they're the right parts. Now, you could spoof these parts, but you'd have to be able to reverse engineer the physics. And basically, probably a rogue state could do that, but probably a CD pirate couldn't. So it's kind of a medium level of security through obscurity. So the idea is, can you build a multi-party protocol such that the system assembles into the correct shape if you have the right control, if you have the right initial conditions, and if you have the right pieces, right microactuators. If any one of those isn't working, you want to assemble into an incorrect state and then detect that. So it's kind of a physical implementation of security. So it's basically sort of a reduction of what we might be able to do. So they're interested in, can you hide a secret using devices like this? I think the jury's still out whether we can really do something like that, but it's interesting to try. So is there an alternative to strong crypto that you can implement with MEMS?
So I think with that rather interesting answer, we shall thank our speaker again. And I want to, before we do that, I want to just encourage you once more, if you do want to be added to the list of announcements of future events on your way out, there's an index card that you could fill out, and we'd appreciate the feedback. So thank you very much.
Thank you for having me.